Hi everyone, I'm Hanwen. Thanks for the invitation from TechBeat and I'm excited to be here. So today I'm going to talk about how to improve scalability for building foundation models of 3D reconstruction. And I will interpret it from three aspects: the model architecture, the training data, and the learning paradigm. So a little bit more about myself. I'm now a research scientist at Adobe Research and working on expanding the scope of 3D vision beyond its traditional boundaries. I got my PhD from UT Austin this June, and this talk is also my PhD thesis. So cool, let's get started. There's no doubt that large foundation models have already changed our lives. For example, I haven't visited San Francisco before, so I can just move my fingers to type what are interesting in San Francisco, and then it will search online and give me beautiful images and detailed travel plan. But all of this make us working 3D vision super jealous, at least for me, because we don't have any capable model like that. Just imagine what we can do if we had a foundation model for 3D reconstruction. This will unlock huge progress in metaverse. We will be able to combine physical and virtual worlds. We will be able to see our families and friends in 3D remotely, do virtual sightseeing, and check online productions with immersive experiences. So what's the reason we don't have them? I would like to say scalability, scalability, and scalability. The scalability are just in the three basic aspects of learning-based method, which are the model architecture, training data, and learning paradigm. So let's first draw a comparison between large models in other domains and the 3D reconstruction models. For example, the language model is built by network architectures with minimal inductive bias, trained on mega-scale data, and require minimum training supervision. However, the current 3D reconstruction models are trying to incorporate 3D inductive bias in model design as much as possible, training on small-scale labeled data, and are dependent on mostly supervised learning with maximum supervision. So how to improve the scalability of 3D models? I would like to say we need to first understand how other domains achieve this. In 2015, the first scalable model architecture, ResNet, was born, and it then just dominated ImageNet quickly. So people proposed larger data to explore the properties and ceiling of it. And after that, this understanding leads to a more comprehensive self-supervised pre-training method MoCo on larger scale data. And the research in NLP actually followed the same route we observed in vision. When Transformer was proposed, it just solved the machine translation problem, which is the main task of that paper. Then people tried to train it with Wikipedia-level data for other supervised learning tasks. And finally, this understanding leads to the birth of BERT and GPT. It seems that this can be a general solution to achieve scalable foundation models. So in the last 2 years, I have been working on this and bringing this foundation model philosophy to 3D for build scalable reconstruction models. And in this talk, I will walk you through my efforts. I will first introduce my work LEAP on minimizing 3D inductive bias. And I will also briefly mention LVSM, and that is a large project I participate at Adobe. I'm not the first author, which further extrapolate the same idea. And then I will introduce my work on scaling data, which are motivated by the performance pattern of previously proposed models. And I will present how we can leverage both semantic and non-semantic aspects of 3D reconstruction to scale the data. And finally, I will introduce my recent work, Razor, which minimizes the training supervision by exploring self-supervised learning. Due to the time limit, I will spend more time on LEAP and Razor. I will also include some details of LVSM because we will later use that for building Razor. And I will quickly go over other works for scaling data and give you some flavor of it. Okay, let's start from LEAP for minimizing 3D inductive bias. When we are talking about inductive bias in 3D models, it can actually be tracked back to decades ago on multi-view geometry. This theory has told us how to correlate 2D and 3D space with projection, and how to correlate 2D and 2D space with epipolar geometry. And all of this inductive bias are reliant on some camera representations. And in the past, this inductive bias has led to the glory age of 3D reconstruction, where we build structure from motion based on them. Concretely, we use epipolar geometry to solve cameras from 2D correspondences. And then we use triangulation, which is the inverse of projection, to get geometry. And these inductive bias are inherited by current learning-based models, where we still link up 2D and 3D by using projection, and we also use epipolar geometry for 2D feature fusion. But the question is, with current powerful models, are these inductive bias are still necessary? And are they still the optimal strategy for learning-based models? Now, let's have a closer look at the example of using projection to correlate 2D and 3D space. Typically, they project 3D points onto 2D images use camera poses, and then they aggregate information at the projected location as the 3D feature. However, if the pose is even slightly off, the projection will be incorrect, and this mismatch leads to inaccurate 3D features and wrong reconstruction. Thus, the model will be very sensitive to pose errors, and this is evidenced by experimental results. For example, in both PixelNerve and my prior work, Forge, we observed that even a 5-degree rotation error can lead to 4 dB PSNR drop. To solve this problem, we have to rethink the definition of camera poses. As we discussed before, camera pose is a powerful concept, but it is not robust. It encodes too many geometric priors, such as rigid body assumption. And additionally, the poses are in compact, low-dimensional representation under this assumption. For example, in a 2D transformation case here, the pose is represented by a 2x3 matrix with just 6 numbers. And this will make it very sensitive. Even a small numerical error can cause large global transformation errors. And instead of a global pose representation, a more robust alternative is to use local correspondence-based approach. Correspondence is a local and fine-grained representation defining the point-to-point relationship between the source and target space. For instance, if we find n correspondence pairs between two spaces, even if some are incorrect, we can still use the remaining correct ones for robust estimation. Thus, we can ground this understanding to build a correspondence-based method for transforming 2D information into 3D space. For a 3D point, we can first initialize its feature. Then, we find its corresponding 2D pixels by computing the feature similarity. Then, their features are aggregated to the 3D points. Thus, this is a pose-free method for relaxing geometric inductive bias. However, this raises an important question is, how do we train this model to find correspondences? This can be very hard, as we define the correspondence as the one-to-one mapping between the 3D and each image. Thus, we might need some non-differentiable operations, for example, argmax, to do ranking. Thus, a better choice is a softer differentiable method. Instead of finding a strict one-to-one mapping, we can calculate the similarity between each 3D points and all 2D pixels. This similarity defines the fusion weights for aggregating 2D information. For example, here, the dark blue arrow has the largest weight, while the gray arrow has the smallest weight. And this operation will create a weight map for the entire image. And we can perform this process for all input images and use the resulting weights for transform 2D information into 3D. And in this manner, we propose a one-to-many mapping, which can be even more robust and easier to learn. And interestingly, in formulation, This computation process is exactly a transformer, or more specifically, a cross-attention transformer layer. Here, the query is the 3D features, and the key values are 2D image information. We compute the similarity between each 3D point and 2D pixel. And using this similarity, we update the 3D features by pulling information from the images. Beyond the transformer architecture, we also need appropriate initialization of the 3D features to compute correspondences. Thus, we use a volume-based 3D representation where each voxel encodes 3D positional embedding to capture 3D structure information. And additionally, we make these embeddings as learnable parameters. During training, they will be updated to encode geometry and texture priors. These are the basic ingredients of our work LEAP, short for Liberate Sparse View 3D Modeling from Camera Poses. From the input images, we first use a shared variety encoder to get their features. Then we transform 2D image information to 3D space using a module with multiple transformer decoder layers. This module has multiple repetitive blocks of cross-attention and self-attention transformers, where the cross-attention transformer updates the 3D volume as we discussed, and the self-attention transformer performs self-refinement on the 3D representation itself. The updated neural volume is then encoded to a 3D radiance field, which supports null view synthesis and training with photometric losses. However, we are neglecting one important problem, which is that the input images are unposed, so which coordinate frame we should use for defining the 3D representation. To solve the problem, we choose one view as the canonical view and designate it with a constant camera pose. We define the 3D representation in the local coordinate frame of the canonical view. To let the model be aware of the choice of canonical view, we find the key is aligning the image features to the feature space of the selected view. Thus, we have another transformer module where we propagate the canonical view features to other views in 2D. Our work LEAP is the first pure transformer-based model for 3D reconstruction, which is concurrent with large reconstruction model from Adobe and is earlier than Duster. LEAP was the state-of-the-art model at the time when it was proposed. So compared with our prior work, Forge, LEAP demonstrates a strong 3 dB better PSNR on null view synthesis for all test sets. Beyond the strong performance, we need to interpret LEAP. Because transformers do everything implicitly, we don't really know how it works and whether its behavior mirrors our motivation for using them. We interpret it by visualizing the attention weights. We first visualize the attention weights of the multi-view encoder between 2D images. Here we have 5 input images, where the first is the canonical view and the red block is the query of the transformer. And we visualize its corresponding attention maps for every other views. And let me show a video. And we find that the attention maps focus on the regions that correspond to the query block. And this demonstrates the emerging 2D correspondences property of our model. We also visualize the attention weights between 3D and 2D. Here, the query is a 3D point, and the attention maps are on input images. We visualize the attention maps of 2 neighbor 3D points with similar index, and they demonstrate similar attention patterns and is consistent across views. We also visualize the attention maps for a far away on-surface 3D point, which demonstrate totally different attention location. And all these results shows that the transformer correctly assigns fusion weights, and this verifies our motivation to use transformers. Based on these understandings, we can view LEAP as a neural version of SFM. Let's take an example of 2 views. The first stage of LEAP calculates soft correspondences of similarity maps between images. Similarly, SFM estimates Hertz correspondences and estimate camera poses. The second stage of LEAP uses the transformer to initialize the features of 3D points. And similarly, SFM uses triangulation to initialize the location of 3D points. Then, LEAP uses multiple transformer modules for iterative refinement of 3D features. And similarly, SFM uses bundle adjustment for this purpose. That is to say, LEAP uses model weights to approximate and accelerate the SFM algorithm designs. But the interesting thing here is LEAP doesn't encode any inductive bias of this computation process. And transformer learns 3D inductive bias automatically from data. So until now, we have talked about minimizing the inductive bias for 2D to 3D lifting. So what about other inductive bias? To understand this, let's get back to the rendering process of the model, where we first want to encode and ideally compress the images to a compact 3D representation. Then we read it out as images when given a target camera pose. Previously, we have minimized the inductive bias in the encoder. However, we still encode many inductive bias in their handcrafted 3D representation and its corresponding rendering equation. So how to design the appropriate 3D representation is always a core problem of 3D vision, and people are always debating on this. For example, only in the last 2 years, we have observed the transition from NeRF to 3D-GS, where they encode different inductive bias and of course have different properties. However, what will be the ultimate 3D representation and what will be the perfect 3D representation? Will we have the answer? So personally, I don't know the answer, but maybe one way to deviate from this debate is using learned 3D representation and learned rendering equation. And this is a high-level idea of the work LVSM. In LVSM, we represent the scene with a set of tokens, and we start from learnable tokens as the scene initialization. When the input images come in, we use a transformer to compress the image information to the latent token scene representation. Thus, what are the important 3D inductive bias to encode is fully learned. With this scene representation, we can render null views under a given target camera pose, and we use a transformer as a fully learned rendering equation. Thus, this is actually the fundamentalism of what we call neural rendering before the age of NeRF in 2016 or 2017, where we only use neural networks to do rendering. Pure neural rendering strikes back. However, we are now still bounded with the concept of scene representation and rendering equation using an encoder-decoder framework. Do we really need them for null view synthesis? Maybe not. Let's just bridge them. And this idea leads to the use of a single stream transformer model, which directly maps the input images to target output. Thus, this model is based on the decoder-only transformer architecture, which mirrors the most scalable architecture that we have observed until now in large language models. And this model is also demonstrate that the multi-view images themselves can be a good 3D or 3D-aware representation. And let me put a pin on this model. We'll later revisit it and use it for build our self-supervised model. So now we have minimized the 3D inductive bias in the 3D models. We improved the model with better architecture, learned representation, and simplified framework. However, this is not the end of story because we're still lacking data to scale this model up. To understand how urgently we need more data, let's look at the following example. For language model, the state-of-the-art models, for example GPT-4, can be trained on 20 trillion tokens. However, if we render the largest 3D assets object-verse with resolution 256 and 20 views per instance will only have 0.02 trillion tokens, which is 1,000 times smaller. So last year, just around April, I was thinking hardly how to improve the scalability of data. And just around that time, Alyosha visited UT and gave a talk saying we are still not giving data enough credit. This talk just clicked me and I resonate a lot with this. I can't agree more. So I would like to say data collection, curation, and creation matters and especially matters for 3D in the current age of large models. So to scale the training data, I propose to first understand the reconstruction tasks, or more concretely, the reconstruction tasks when given different number of input images. And on this spectrum, we have two extreme cases, a dense view and single view reconstruction. When we have a lot of input images, the reconstruction task is actually highly non-semantic or geometry focused. This is evidenced by traditional non-learning based method like structure from motion, where we use SIFT to get image key points, we use Loess ratio tests to get correspondences, we use epipolar geometry to get camera, and we use triangulation to get geometry. There's no semantic involved. Thus, we can leverage this non-semantic aspect to create and synthesize mega-scale data as our work MegaScenes. Here, we represent the scenes with basic spatial structure and geometry, and we eliminate the scene semantics like object category affordance when we generate the data. This benefits us with a highly scalable procedural generation method, where we first get scene floor plan, and we assemble shape primitives into objects, place them into the scene, and sample texture to be either specular or diffuse. And we randomly sample the lighting, and finally render at random camera locations. Thus, there's no learning happens here, and we can just run this simple script to get synthesized the data that is much larger than the real data in several days. They are just a free lunch to improve your model. And on the other hand, the single view reconstruction is actually very semantic related. And this is related to early studies of recovering geometry from 2D ages. And this is a geometrically ill-posed problem because we will have infinite number of solutions. But why humans can do this? Because we know semantics. We know the thickness of a laptop is very thin because you know that's a laptop. Thus, to make the model generalize better, we propose to learn more realistic semantics from in-the-world data. We first initialize the model with synthetic data, and then select high-quality images from the in-the-world data, and then we perform self-training, where the most important part is a cycle consistency loss. And finally, we perform semi-supervised learning on both the synthetic assets and in-the-world data. We curate about 300,000 instances from 2 million online images. We observe that with more data, the model shows better performance. And this performance gain is consistent across all testing data. So, although Real 3D is a special case for single-view reconstruction, it does show the power of large-scale in-the-world data and demonstrate its possibility to unlock more scalable learning. And this just explains why GPT is so scalable. Because it is trained on internet-scale text data by performing self-supervised pre-training. So for 3D reconstruction, what will happen if we can do similar things? If we can learn from in-the-world videos, we will have enough data to build our foundation models. But to achieve the goal, we need 3D self-supervised learning. And to build this, let's have a look at the self-supervised methods in other domains. So when we check these works, we can find that many of them share the same principle of learning by predicting so-called missing data. For example, In language model, we give it all the words except the last one, and we ask it to predict the next word at each step. So effectively, we leverage the sequential structure of language. And similarly, in 2D vision, we randomly mask some image patches and use the remaining ones to predict and mask the missing ones. And here, we leverage the 2D spatial structure of images. So this inspires us to make an analogy for self-supervised learning for 3D. What will be the missing data in 3D vision? Our answer is the missing data is masked views. Since in multi-view geometry, a view is the smallest unit, just like a word in a sentence or a patch in an image. So we can do self-supervised learning similar to null view synthesis, and let me show you more details. For unlabeled videos of a scene illustrated by these color shapes, we can sample multiple images from it. And we will split the images into two groups. We use one set as the input view, or so-called observed views, for reconstructing the scene. And we use the other sets as the target set, which is hidden, for providing self-supervision. We'll first predict cameras of all views together. And then we use the images and predicted cameras of the observed views to get our scene representation. And then we use the cameras of the target views to render the scene predicted from the observed views. And we will get rendered images of the target views. So we can train with photometric loss between original and predicted hidden target views. Thus, this idea leads to a self-supervised learning framework requiring zero 3D supervision. And this is different from what we called training with no 3D supervision, because a lot of people use this term to promote their works, but they still use ground truth cameras for training. In contrast, we don't need any geometry and camera annotations. And our learning framework is grounded by our model Razor. This model has 3 stages, which are camera estimation, latent scene reconstruction, and rendering, where the model of the last 2 stages is basically an encoder-decoder LVSM we discussed before. So at the beginning, it predicts cameras with per-view camera poses and shared camera intrinsics. As the input images are unposed, we select the middle frame as the canonical view for defining the coordinate frame, which is similar to leap. To predict the cameras, we leverage a so-called camera token, which is learnable. We replicate the camera token with the number of input images, and we add image index embedding to them and also the image tokens, letting them correlate with each other. Then we use a camera estimator, which is a transformer model to update the camera tokens. And finally, we use an MLP to predict this camera information. And importantly, here, the cameras are in low-dimensional representation, for example, quaternion for rotation, and translation with 3-dimensional vectors, and also 2 focal lengths for the camera intrinsics, which help us disentangle seeing information from it because it has limited capacity. We then convert the cameras into Planck array maps as it provides fine-grained ray-level information to help reconstruction, similar to our discussion on pose in the part of leap. We then split the images into 2 sets as we discussed, for the input observed set and the hidden target set. From the observed views, we compress them into latent token scene representation. And we use the predicted cameras to query the scene representation and render target views with a transformer. And finally, we compute the photometric loss and perform self-supervised learning. And again, I would like to emphasize that Razor is trained with zero 3D supervision, no camera, no geometry, and just the images losses. And the model is built on pure transformers with minimal 3D inductive bias, giving the freedom to the model itself to discover useful patterns from raw data. For experiments, we compare Razor with Oracle self-supervised methods. This Oracle method takes camera annotations for training and also requires camera annotations during inference. In contrast, our Razor is a fully self-supervised model. During both training and inference, it only takes 2D images. We perform experiments on 3 datasets with different scene and camera settings. Importantly, we have DL3DV and real estate annotated by CoMap, and on Observers, we have the ground truth cameras as is synthetic. Surprisingly, we find that Razor achieves comparable performance with the Oracle method LVSM. And it's shocking that Razor actually outperforms LVSM on DL3DV and real estate. And this is very counterintuitive. Do we really have seen any self-supervised method outperform their supervised version when the training labels are perfect? No. So actually, the reason is that CoMap annotation is noisy. Here are 2 pieces of evidence to support this. First, on Observers where we really have perfect camera annotations, we perform on par but slightly worse. And the second evidence is visualization. Here I demonstrate one example of Razor outperform the 2 baselines, where the baseline performed worse on the glass regions. And this is not a coincidence. We find that the Oracle method GSLRM and LVSM consistently fail on some cases. Interestingly, these cases are the scenarios that CoMap usually fails. For example, the glasses in the first row, the high luminance intensity, and white walls in the second row. These results are strong evidence to show that the problem of supervised training with CoMap pseudo-labels. People think CoMap is perfect, but actually it is not. If you train your model use CoMap's annotations, that's just a distillation of noisy CoMap. And we need self-supervised learning to break free from it. And let me show you more results on null view synthesis. And you can see that even though trained without any 3D supervision, our Razor model performed well on large camera baselines, scene structures, complicated lighting, and material very well. And here are some more results. So except from null view synthesis, we also inspect Razor's predicted camera pose space. And we show some visualization results here. And you can see Razor's predicted poses can capture the camera motion. For example, in the first example, it first faced toward left and it gradually turned to the right. However, we also noticed that the learned pose space does not strictly match the real poses because our reconstruction operates in the latent space. So to understand how much pose information is actually learned, we probe the learned pose latent space. And here, we use a frozen camera encoder initialized by our self-supervised pre-training, and we train a prediction MLP on top of it using pose supervision. And we also compare with a baseline, where both camera encoder and prediction MLP are trained from scratch using supervised learning. And our experiments show that our self-supervised camera encoder achieved better performance. And this result verifies that Razor does learn meaningful camera pose space. And our pose self-supervised learning objective is more efficient than supervised pose loss. Thus, the takeaway of Razor is that we can train it with self-supervised learning, no camera labels, no geometry supervision, just image losses. And in particular, I also want to show the similarity between Razor and video generation model more philosophically, because both of them have minimal or no 3D inductive bias, no 3D aware architecture, no 3D representation, and no rendering equation. And both are trained with pure self-supervised learning with no 3D supervision. But both have emerging 3D awareness. And importantly, our self-supervised learning enables us to have unsupervised 3D controls of camera viewpoints. And this understanding of this discussion naturally leads to some future work, and let's go back to the 3 axes. Video generation is so scalable because it can do self-supervised learning on any interval videos. However, we can only work on static 3D scenes, which naturally leads to much smaller training data. Thus, to achieve more scalable learning by using larger data, we need to model dynamics, or so-called 4D. So this is another reason why 4D matters, because 4D does not only unlock new capability, but also help us scale. And on the other axis, Razor operates in the latent space, but is not fully geometrically correct, and we need to keep a better balance between scalability and geometry correctness. And importantly, we need to build a unified model taking all 3 aspects into consideration, and this will help us to build a world model with correct understanding of physics to augment text-based intelligence and help robotics. That's all of this talk. Thanks for listening.